Hi guys, welcome back to my channel. So in today's video, I'll be discussing about my project EEG based motor imagery classification. So the main motivation to do this project is, let's say we have some individual who has some motor disabilities and he wants to communicate effectively. So we need a non-invasive and a cost-effective approach. So we thought to develop this project. So the main idea of this project is to use the EEG signals which is coming from the brain to identify when a person imagines their left or right hand, we need to predict that what he imagined using the EEG signals. So these are some prerequisites which we need to know. So the EEG signals which is developed by our brain has many waves which are delta waves, theta waves, alpha waves, beta waves, gamma waves. Let's say when we are in deep sleep, the delta waves get produced and so on. So for our project, we are more focused on alpha and beta waves only. So they lie in the 8 to 13 hertz and 13 to 30 hertz bands. Now, how we achieve this? So basically, what we need, a person tries to imagine moving their left or right hand, and we need to predict that using EEG signals. So when a person imagines any movement of his hand, there is a change in the power in the alpha waves and the beta waves. So we need to basically capture that power and then take a decision using a ML model. So as we can see, there are some event related desynchronization. That is, there is a decrease in power during movement imagination. After that, again the power gets increased. So for that, the three channels which we'll be using at C3, C4, and CZ is like a ground channel. So as you know guys, when we try to imagine moving our left hand, it's basically our right part of our brain gets activated as they are connected in opposite way. So in either case, like to measure the left hand movement, we need to see the right hemisphere. Further, we have C4 channel, and to measure the right hand movement, we'll see the left hemisphere by the C3 channel. So by using both the channels, the main or the core idea is to find the power difference in this alpha and beta waves. Here the mu is nothing but it's a sub part of the alpha waves only. So basically we need to find the power difference and then take the decision. So how we solve this problem? So first we'll load the calibration file or the dataset file and we set the artifact threshold. So what is artifact threshold? When we measure the EEG signals, we get a lot of noise like our heartbeat, eye blink, etc. They all produce or add some noise. So we keep a certain threshold and reject the signals which is above the threshold because we know that they are not a part of our goal. Then we take the 20 seconds signal and split it in a time window of zero point 0.5 to 5 seconds. That's called approaching because we analyze the signal in this time window and take the decisions accordingly. Then we give it to a band pass filter. It is generally a Butterworth filter of order 4. After the filtering is done, we give it to an eigenvalue problem where we solve the eigenvalue problem to get our features. Now I'll explain it in a more detail. So basically we have a data set, the filter data set which is coming from the Butterworth filter. What this eigenvalue does is, it's basically does the CSP concept where this data set, but in the original data set, it is very difficult to take the decisions because the C3, C4 channels are very aligned to each other. Like we can't see the difference. So what we do is we project them to another space where in the x-axis C3 channel power gets maximized and C4 power gets minimized, and in the y-axis C3 channel power gets minimized and C4 channel power gets maximized. So we transform it to another space where we can take the decision easily. So the power is calculated after basically after this eigenvalue problem solving, we get the new data set, which is the transformed version. On that, we apply log. Like variance is basically power. So we measure the power and take log of it. This we take as a features to train on our ML model. And after that, the K-fold cross validation. These all are the standard ML training techniques. The model which we use is LEA. Next, this is a pseudocode. So we use the concept called, as I said, FBCSP, which is the extension of the CSP concept, which I have explained earlier. So it's just the CSP, we just apply it in individual frequency bands. Like the whole band, the Butterworth filter gives us, let's say, the range in 8 to 30 Hertz. We again divide it into subbands and apply CSP on each band to get the accurate results. So basically we do the normalization and we give to the eigenvalue to solve. After that, we take the log normalized value as a feature and then train our model so that we can take decision. So these are the results which we got. We tested on the 4 files which is given in that website. The accuracy which we got is 81%. The kappa is 0.614, 615. So these are the resources. So this is the competition link. I will, yeah. So this is the competition where we can get a data set. So this link I'll keep in the description of this video. You can see the data set or collect the data set from there. So I'll try to explain the MATLAB code. So you just load the dataset which you downloaded from the website into your MATLAB folder, and then basically load the folder in your workspace. After that, I have created a trial length, as I said, 0.5 to 5 seconds. This is the epoching. Basically we split into the time window of this duration. We have set the amplitude threshold to the artifact removal, and these are the frequency bands. As I said, 8 to 30 Hertz range will divide into many frequency bands, and these are target channels. Basically, we load the files in the .mat format, and after loading, we basically, in this part, we check for the channel C3 and C4 because that dataset contains a lot of channels, but we are interested only in the C3 and C4 channels and the CZ. So we extract those channels only. And this is the artifact threshold where we set the threshold and remove the signal which is more than this. And in this part, basically we look for the labels. Basically we find the labels where the data is starting and the data is ending. In the data, in the website, there is a clear description about it, how the files dataset are given. So basically they have a start position and an end position marker. So we need to extract those labels. After that, this is basically the artifact removal. As I said, if the epoch or the time window is greater than the amplitude threshold, we just remove it and increase the rejected count. So in that way, we do the artifact removal. Next, we basically sort the data set, and then comes the FBCSP part. Basically, first we normalize and find the covariance. Covariance is almost similar to a power. Here we find the covariance for both the channels, and then we give it to the eigenvalue problem and try to get the solutions for it. So we can use the inbuilt function. Then we take the first and the last solution from it, as that corresponds to the C3 axis where C3 is maximized and C4 is minimized, and the last corresponds to the axis where C4 is maximized and C3 is minimized. So that solution we again normalize, and this becomes a feature. On this feature, we train the ML model. Like from here, it's the standard K-fold ML model training code. So this is all the training part. The model used is the LEM model. So this is the results on all the 4 files, the voltage and the threshold what we get. So these are the individual accuracy for all the files. So the mean accuracy, and this is the mean kappa. These both are basically the figure of merit for our work. Basically our algorithm is 80% correct. These both are a figure of merit for the classification. By seeing the mean accuracy, we can say that the algorithm is nearly 80% correct, and kappa is also a figure of merit, where we prefer a kappa to be more or close to 1. So it's a decently good kappa. Thank you so much guys for watching this video.